Hey class, today we're going to be doing section 7.26a, which is our inference for linear regression. Today in this unit, or in this lesson, we're only going to be looking at the conditions to do this inference, and then in the next lesson, I'll go through an actual hypothesis test for regression. So recall that a linear regression model models the linear relationship between two quantitative variables. You determine the equation of a sample regression line, and in this section, we're going to write y hat equals b sub 0 plus b sub 1 x. It's the same as our y hat equals a plus bx from chapter unit 2. We're just going to write it slightly differently. And this is given a sample bivariate data set, and then interpreted the slope, which is B1, and y-intercept is B0. So we did all that stuff back in Unit 2. Every sample statistic corresponds to a specific population parameter. This also applies to the intercept and slope of the equation of a sample regression line. So the equation of the population regression line can be rewritten as mu sub y equals beta sub 0 plus beta sub 1x, where mu sub y is our population mean of y for a specific x value. B sub 0 or beta sub 0 is the intercept of the population regression line, or the y-intercept, and beta sub 1 is our slope. It is unreasonable to expect every y value for a specific x value to equal the corresponding population mean for y, or mu sub y, due to variability. So we know all about sampling variability. Not every sample is going to be the same. It all varies, so we can't expect it to be perfect. Therefore, we account for each individual y in the population by using mu sub y equals beta sub 0 plus beta sub 1x plus e. And e is the error or residual of the individual y value. So we're kind of accounting for that slight error that might happen based on sampling variability. The mean of every y distribution for a specific value of x lies on the population regression line. So you can kind of see this in that picture. Looks kind of funny with the little histograms all the way up, but the mean of that value for each one of those distributions is going to lie on that regression line. And we will use linear regression sample statistics. So this is our b sub 0 plus b sub 1, or I shouldn't say plus, and b sub 1, to make inferences about the corresponding population parameters, which is beta sub 0 and beta sub 1. And with every inference we studied thus far, we have assumptions and conditions. Now, in this unit, the conditions are kind of insane. So there's 6 of them, which is way more than what we usually have. So on the AP exam, I've never seen the AP College Board ask you to do conditions and a linear regression test in the same problem. They're either going to ask you to do the conditions, or they're going to tell you the conditions are met and to do the inference. So we need to know both, but don't freak out. You won't have to do both of them in one problem on the AP exam, most likely. All right, so our assumptions and conditions, we have, first of all, when we get to this, just know it's really important that a sketch is required for any display that you reference. We're going to reference the scatter plot, the residual plot, and the histogram of the residuals. So I'm going to show you in the graphing calculator how to get each one of those today. We have a linearity assumption. So I'm just going to kind of briefly cover all these. So the scatter plot has to be reasonably linear. If not, we can re-express the data, which if you don't remember how to do that, go back to Unit 2 and look at that. We have an independence assumption. So for this one, you're going to kind of just think about context. So based on context, is it reasonable to assume that the observations are independent from each other? We have, and I number these a little differently. I number this one as 3, 3, and this one is 4, and this one is 5. So I just kind of go through, make sure I have all 6. So 3, we have a randomization condition as usual. If we don't have randomness, then we say that it's a good representation of the population, assume it. 4, we want a random residual condition. So the residuals or errors must be mutually independent. And when we talk about this specific condition, we want to make sure to mention that statement there. we're going to justify that statement by looking at the residual plot and making sure it looks random, that there's no patterns. But then we want to say, if that's true, thus the residuals are mutually independent. So don't forget to write that piece of it. Specifically, when X is related to time, we don't have mutually independent residuals because one day's errors will affect or could affect the next day's errors. So what we want to do is we want to just notate that potential violation. Just kind of say something about X is time. So technically the residuals might not be mutually independent, but then reference your residual plot. And if it's random, you can say, we're going to assume that, or that the plot suggests that the residuals are independent. Our fifth one here, the equal variance assumption. So the variability of Y should be about the same for all values of X. We can refer to the scatter plot for this assumption. We want to make sure that there's equal or constant spread around that line, that there's no fanning out or thickening around our line. And then our sixth condition here is our normal population assumption. At each value of X, the distribution of the residuals needs to be nearly normal. So we can use a histogram of the residuals, which I'm going to do. You can also use a normal probability plot, but I like the histogram a little better because I can really see that shape. All right, so let's look at an example. A college admissions counselor was interested in finding out how well high school grade point averages predict first-year college GPAs. A random sample of data from first-year students was reviewed to obtain high school and first-year college GPAs. The data are shown below. So in your graphing calculator, the first thing you're going to want to do is go to Stat, Edit, and then I've already loaded all of my numbers into L1 for high school GPA and L2 for first-year GPA. So you're going to want to pause the video, put those in your calculator so that you can play along. And then if you notice in the notes, there's these summations. This is just for you to check to make sure you've got all those in there correctly. So you can go to Stat, Calc, go to 2var Stats, and then I have my lists in L1 and L2. This is just simply for me to check. So my sum of the X values is 58.49. So that checks out. And then 51.532 for my Ys. So I know that I've put all those values into my calculator correctly. Now we're going to determine if the assumptions and conditions for a statistical inference are met. So the first thing we want to do is graph the scatter plot. So I'm going to go to my stat plots. I'm going to make sure that they're all off. You can hit 4 and enter is an easy way to turn them all off. Then go to plot 2. I'm going to turn it on. And then go to the scatter plot, L1, L2, and then I'm going to go to zoom. Oh, actually, go back there for a second. Did I put my regression equation in? No, not yet. Okay, so then I'm going to go to zoom and then 9 for zoom stat. Now, I have my line in here. That's because I already ran my linear regression. So if you want to see the line in there, which I usually find it easier to draw my scatter plot if I see the line, and then I can see if there's any thickening or fanning out. I really do like that line. You can do it a couple ways. You can go to Stat. You can go over to Tests. Tests. And then go all the way down to the bottom of the test or bottom of the list. There's a lin reg t test. So this is our linear regression t-test. You can also just go and run your linear regression. But I since we're doing the test anyways, I'm going to run this. L1, L2, I don't know if it's going to be less than or greater than 0 because I wasn't really given any context information here, or if it's going to be not equal to. I don't really care. But regression equation, I can hit vars, go to yvars function and 1, and that'll put it in Y1 for me. So it'll run my regression, it'll calculate my residuals for me, which we need when we do the residual plot and the histogram of the residuals. So you're going to need to do this anyways. And it'll put my line in Y1, so it'll graph it. So I'm going to calculate that. It gives me a whole lot of information here, which I'm not going to use right now for the conditions. We'll see this tomorrow, or not tomorrow, but in the next lesson. You can also just go to Stat, Calc, and then go down to one of these linear regressions. You can do this as well and get your regression equation here. It'll do the same thing so you can get it on your graph. All right, so now I'm going to draw this. I usually just kind of sketch it really quick, and the line definitely helps me figure out where these all are. so that I can make it look as close as I can. Something. And last 2. Okay, so something like that. Now, for our conditions, so the first one is linearity. So I want to make sure that's the scatter plot. So the scatter plot of the high school GPA and first year GPA is reasonably linear. And all we have to do is make sure to draw our scatter plot there to show that. Number 2 is our independence. So it's reasonable to assume that each student's high school GPA and corresponding first year GPA are independent of the GPAs of other students. So that's an easy assumption to make. Our third one here is our randomization. And in this problem, it said a random sample. So it is stated the sample of first year students was randomly, I spelled that wrong, randomly selected. Okay. I ran out of room here on my paper, so I'm going to go to the next page. My next condition, I need to talk about the residual plot, so which means I need the residual plot. So what I'm going to do is I've already I've run my linear regression. You need to run your linear regression before you can get your residual plot. I'm going to go back up to stat plot. I'm going to turn my plots off. So I'm going to go to 4 and turn them off. So I don't have to go in and do it. It's just an easy way to make that happen. Then I'm going to go down to plot 3. I already have it set up for residuals. I'm going to turn it on. My X list is in L1. And if you don't have the word residuals here, to get that, you go to second stat to go to the lists. And then down at the bottom, number 9 is going to be residuals. So that'll get you that. Now I'm going to zoom stat again to see my residuals. Notice I've labeled my graph as residuals and high school GPA. And I'm just going to quickly sketch these residuals as best as I can. Something like that. Okay, so there's my residuals. And our residual plot appears random. There's no distinct pattern. It looks pretty random. So it is assumed. So this is the other part. You can't just say that it's random. You have to say what that means. It is assumed that the residuals are mutually independent. So the residuals aren't affecting each other. Our 5th condition, the scatter plot does not display a fanning out. So what that means is if it was like all the points were clustered near the line and then they all started getting farther and farther away as X increased, that sort of thing. Or thickening, so same kind of thing, thickening around the least squares regression line. So it's assumed that the variability of first year GPA is the same for every high school GPA value. And then the last one, our 6th one, is our normal population condition. We need to check the residual histogram. So I'm going to go back to my stat plots. I'm going to turn my plots off, go back. And then my first one here, I have for histograms, I'm going to turn it on. And again, in the X list, there's no X and Y, so it's just residuals. If you need residuals in there, you hit second stat and then go to the bottom of the list there for residuals. I'm going to zoom stat. And there's a line down here because I didn't turn off my Y1 line, linear regression line, but we can just ignore it. So I'm going to quickly sketch a picture of this histogram. Okay, and the histogram of the residuals, notice I have my histogram labeled as residuals, is not significantly skewed. So it is assumed that the distribution of the residuals is nearly normal. Okay, And that is it for the conditions. I know it was a lot. There are 6 of them, and you just got to practice to make sure you get them all. Make sure you draw those graphs to reference. And in the next lesson, we'll actually run through a linear regression t-test. All right, and that's it for today's lesson.